Hello my dear student friends, welcome you all to this video lecture series of network analysis. In previous lecture we had a discussion about the voltage across or the frequency at which the voltage across inductor and capacitor will be maximum, right? So we'll see one problem based on that, and also we have seen the derivation of the relation between the bandwidth, resonant frequency and quality factor, right? So we'll see a problem based on that, and then we'll go to new concept. Okay, fine. So let us discuss the problem. So you have been asked a question. What is the question? Determine the quality factor Q of a coil. Okay, so you need to find out Q. Okay, for the circuit, for the series RLC circuit, which is consisting of R, L and C. Also let us find out the bandwidth. Okay, so let us find out the bandwidth. Okay, fine. So for that purpose, what we need, okay, what we need to find out Q. Okay, let us write the given first. So which are the given terms? Given terms are nothing but R is equals to 10 ohm, L is equals to 0.1 Henry, isn't it? And capacitor is having 10 microfarad. Okay, so this is not visible to you people. Okay, so this is 10 microfarad actually, right? Fine. And which values we need to find out? We need to find out first it is Q. Okay, in order to find out Q, we must have to find out FR and bandwidth. Until and unless if we are not going to find out the resonant frequency and bandwidth, we cannot find out Q, because Q has a relation as Q is equals to FR upon bandwidth, right? So until and unless we are not finding out FR and bandwidth, we cannot find Q. Okay, so ultimately it is indirectly asked to find out FR and bandwidth. Is that fine? Okay, so let us check it out. Fine. So first is nothing but your FR. Okay, so you know the formula to calculate FR. FR is equals to 1 upon 2 pi root LC, right? So put the values of L and C in this particular equation. You will be getting the value of FR as 159.15 Hertz. Okay, fine. So once we have got FR, now let us calculate bandwidth so that we can compute quality factor Q. Okay, so we have derived this equation, right? So bandwidth is equals to F2 minus F1, right, is equals to R divided by 2 pi L. This equation we have derived in the previous lecture itself. So this you need to remember, right? Okay, so bandwidth is equals to R divided by 2 pi L. Okay, so put the value of resistor and inductor in this particular equation. You will be getting the value of bandwidth. And after computing the value of bandwidth or calculation, after performing this calculation, you will be getting the values as value of bandwidth as 15.91 Hertz. So that is the bandwidth of our series RLC circuit now. Okay, so right now we have computed FR and bandwidth. Now let us take the ratio of these two, then we can get the value of quality factor Q, right? So let us take the ratio. So Q is equals to FR upon bandwidth, right? So we have computed FR. What is FR? Is 159.15 Hertz and bandwidth is 15.91 Hertz. So if I am going to take the ratio, I will be getting value of quality factor Q as 10. Okay, so this is a very easy example. Okay, so only you need to remember this formula. This is very important. Once you remember this formula, you need to remember the bandwidth formula, and you already know that what is the formula to calculate the resonant frequency. Okay, so once you are going to find out the resonant frequency, bandwidth, you can easily find out the value of quality factor. So such kind of problems may be asked for 8 marks. Okay, if there is a theory question. Okay, fine. Now let us go for the next point. That is nothing but different types of. Okay, let us go for quality factor first. Okay, now we are going to derive the equation for quality factor Q. Okay, so deduce the expression. Deduce means derive the expression for quality factor Q. Okay, fine. So what is quality factor? Quality factor Q is a ratio. Already we have seen what is that quality factor. So quality factor Q, it is the ratio of reactive power, right, of inductor or capacitor. So quality factor is associated with inductor as well as capacitor. Remember this one. Okay. So it is the ratio of reactive power of inductor or capacitor to the true power in the resistor, right, which is in series with the capacitor or coil. Okay. So remember that we always used to connect the resistor in series with the inductor, right? We'll see in the later portions. Okay. So till then you just remember that we need to connect the one series resistor with the capacitor and inductor so that it will work properly. Okay, fine. Okay, so let us write this as in terms of equation. So Q is equals to 2 pi multiplied by maximum energy stored in either inductor or capacitor, okay, and energy dissipated per cycle by resistor. Okay, now let us discuss about inductor. So what will be the maximum energy stored by the inductor? It is given by half Li square. Okay, you might have studied this equation in the first year itself. Okay, so remember that maximum energy stored in an inductor will be, it is half Li square. Okay, so this is the maximum energy stored by the inductor. Okay, and energy dissipated per cycle is given by I by root 2 into RT. Okay, so this is nothing but energy dissipated by resistor. Remember this thing. Okay, so it is I by root 2 bracket square R into T. Is that fine? Okay. So these are some basic questions, basics terms that you have already studied in the first year. So I am not going to discuss these terms again. Okay, fine. Great. Now let us put the equations in this particular equation. Okay, so now let us put this, okay, half Li square at the numerator and let us put this into the denominator. Okay, yes. So it is nothing but it is square of this one, no? So fine. So half Li square we have put it over here into the numerator, and I by root 2 bracket square was there, so I square divided by 2, right? So root 2 has been getting cancelled with this square. Okay, and RT, isn't it? Okay, so can I cancel out I square? Yes, I can cancel out. Can I cancel out divided by 2? Yes, I can cancel out. And what is the relation between T? T is nothing but time. Okay, so don't consider this as temperature. Okay, T is nothing but time. What is the relation between time and frequency? They are inversely proportional to each other. So can I write it? T is equals to 1 upon F. If I am going to put it T is equals to 1 upon F over here, can I take this term to the numerator? Yes, definitely, because it is divided by, again, divided by F, right? So that is going to come to the numerator side. Okay, so because of that we have taken that term F to the numerator side. Okay, and now 2 pi FL, what is that 2 pi FL stands for then? Okay, so 2 pi FL is nothing but omega. Am I right? Is it 2 pi FL is equals to omega? Or rather 2 pi F is omega, no? 2 pi F is omega, and therefore Q is now representing XL divided by R, because XL is nothing but what? Omega L divided by R, right? So I hope we had a discussion about what exactly the quality factor. Okay, so we had a discussion about Q is equals to quality factor is equals to XL divided by R. We had a discussion about it, and right now we have derived it. Okay, so similarly Q for capacitor will be what? It will be XC divided by R. But what is XC? XC is equals to 1 upon omega C, and this R is as it is into the denominator. So remember that now we are going to derive this one. Got it? Okay. So similarly, let us go for finding out the quality factor of capacitor. Okay. So similarly, in case of capacitor, maximum energy stored is given by half CV square, and the energy dissipated into the resistor will be same. It will not change, right? So I by root 2 bracket square into RT. T is nothing but time. Remember this. So therefore, now let us put the equations into the particular equation of Q. Okay. So half CV square we have inserted over here, right? And then let us insert this at the denominator. So can I cancel out divided by 2? Yes, I can cancel it out, right? Okay. Then what is V? Okay, V is nothing but what? Okay, let me just. Okay, V is nothing but IR, right? So therefore, we are going to put it in terms of R is nothing but what? XC, right? So therefore, V is equals to, right now we are finding out the voltage across capacitor, right? So for that purpose, V is equals to IR, and resistors offered by the capacitor is nothing but XC, right? So can I write I into XC? Yes. And what is XC? XC is nothing but omega C, right? And this has to have square. So can I write a square for this one? Yes. So we have inserted over here. Got it? So instead of V square, we have inserted I divided by omega C. It's a bracket square. So that's why it is going to become I square divided by omega square C square, right? So one C we can cancel out with this one C. Okay. Let us do this. Okay. So I square we have cancelled out over this I square, and this 2 will be cancelled with this one, right? Okay. So now let us check out for further. Okay. So this C we are going to cancel out with this single C, because C square is there, right? Omega square will be as it is, right? Now again T we are going to replace with 1 upon F, right? So this 1 upon F is going to go appear into the numerator, right? And now let us connect this F, or let us write this F after 2 pi. Okay, so it is going to become 2 pi F, right? And into 1 divided by omega square CR. It will be as it is, right? So R is going to get connected over here, because this is coming into the denominator. Yes or no? Okay. So this is nothing but 2 pi F divided by omega square C into R, right? What is omega? What is 2 pi F? It is omega, right? So can I write it as omega? Let us write it. Okay, so this omega and this single omega will get cancelled out, and therefore it is going to become Q is equals to 1 upon omega C into R. What is 1 upon omega C? It is nothing but XC. So is it XC divided by R? Yes, definitely. So right now we have computed, or we have derived the equations for quality factor of a coil as well as quality factor of a capacitor, right? So remember that Q will be associated with respect to inductor as well as capacitor. Okay, so simply remember that it is the ratio of reactance to the resistance. Okay, so reactance of inductor is what? It is XL, and reactance of capacitor is what? It is XC, right? So XC divided by R will be the quality factor of a capacitor, and XL divided by R will be the quality factor of a inductor. This is as simple as like this. Okay, fine. Now let us go to the next point. Okay. Now let us see the different type of resonance now. Okay, so we have seen right now, up till now we have seen a series RLC circuit, whatever the concept what we have discussed So far, those were related to the series RLC circuit. Okay. Now let us go for the another type of circuit which can generate the resonance. That is nothing but parallel resonance. Okay. So parallel resonance is consisting of inductor and capacitor. Remember that the resonance will not occur if there will not be any resistor, if there will not be a inductor or capacitor. Until and unless these two components are not there, definitely the resonance will not occur, because the phase angle has to be nullified. Okay, then and then only the resonance can occur, because the maximum current can flow if the phase angle of these two components are going to become equal in magnitude but opposite in sign. Then and then only their phase angle will get zero, and then in that case the applied voltage and the current flowing through that circuit is going to have a zero phase shift, or we can say that they are in phase, and then only the maximum amount of current is going to flow through that particular circuit, right? Okay, so parallel resonance is nothing but there is a one resistor which is in series with the inductor, and there is one resistor which is in series with the capacitor. Okay, so this is nothing but my circuit parallel. Okay, they are connected in parallel, so that's why this kind of circuit is called as a parallel resonance. Okay, right. So this is nothing but my supplied voltage. Okay, this is L, and this is also called as JXL, and this is also called as minus JXC, right? And remember that whenever the parallel combinations comes into the picture, your admittance term will come into the picture. Yes, so if it is in series, definitely the impedance or the series kind of connection, that is nothing but R1 plus R2, that kind of a equivalent we are going to find out. But whenever the parallel connection is going to come, definitely in that case we used to go for admittance. Okay, so as like that your series RLC circuit, here also the impedance or the phase angles has to be matched. Okay, that means your XL and XC must have same values, so that the phase angle nullification will occur, and because of that the maximum amount of current is going to flow, which is again in phase with the applied signal. Okay, so that is also again same thing. Okay, so basically parallel resonance occurs when the same condition, if your XC and XL, if it is matching or if it is becoming equal, then and then only definitely the parallel resonance also occur. Okay, the frequency at which the resonance occurs, that is called resonant frequency. That also we know that the two branch currents are equal in magnitude, but if they are opposite in phase with each other, therefore the two phase shifts get cancelled each other, and the total current becomes, sorry, okay, yes, if both the phase angles are having 180 degree out of phase with each other, that means let us say this is having a 90 degree and this is having a minus 90 degree. So what is the total phase difference? It is 180, right? So because of that, the total current flowing through the circuit, it is going to become zero. Okay, that means minimum current is going to flow if there what we can say, they are out of phase by 180 degree. Okay, but we want a maximum current. Fine, so for that purpose we must match their phase angles. Okay, fine, that means we need to have zero phase angle between these two, right? If it is having 90 degree, then it has to be have plus 90 degree, and then only we can say that the phase shift is zero and maximum amount of current is going to flow through the circuit, right? So that is the meaning of this particular sentence. Okay, so let us discuss the saying, and let us derive the equation to calculate the resonant frequency of a parallel resonant circuit. Okay, fine. So over here we discussed that if the series resistance is there, then we can say that Z1 plus Z2 we can directly take. Okay, but as there we have taken the parallel combination of these two. Okay, so therefore let us say this is nothing but my z1 and this is nothing but my z2. Okay, so let us say z1 is equals to r plus rl plus jxl. Okay, and z2 is equals to rc plus, sorry, not plus, minus jxc, right? Okay, and as they are connected in parallel, we have to take their admittance. So 1 upon rl plus jxl and y2 will be 1 upon rc minus jxc. That's it. That is so simple. Okay, so we have first found out the impedance of this particular, let us say, series arm. Okay, let us say this is the impedance of my series arm. Okay, and this is the impedance of the other series arm which is parallel to the first one, right? And then we have found out their impedance, admittances, right? Then we have taken their inverse. Simply we have taken the inverse, right? Okay, or so rather we can say that it's a reciprocal. Okay, instead of finding v divided by I, we have found out I divided by v, right? And that is nothing but my admittance. Okay, fine. Now let us add these two admittances, right? Because they are connected in parallel, right? So their respective admittances we have found out over here, right? The impedances we have found out over here and their respective admittances. Their total admittance can be found out by adding these two admittances, these two branches admittances. So therefore y is equals to 1 upon y1 is nothing but what? This one. So we have inserted this. What is y2? Y2 is this one. So we have inserted this one. Then what we are going to do? We are going to multiply by its complex conjugate. Multiply and divide by complex conjugate of this one. So what is the complex conjugate? The middle term is going to get altered, right? So if it is plus, we are going to take the minus sign and we are going to multiply and divide by this complex conjugate, right, to this particular term. Similarly, in this case also we have taken the complex conjugate, that is nothing but this one, that is plus, and we have multiplied by and divided by the complex conjugate. Okay, fine. Now let us compute the further things. Now let us expand the bracket and find out some relation. Okay, wait a moment. Okay, so let us expand this. So let us expand the denominator brackets, right? So this is nothing but simply a plus b into a minus b form, right? So can I say that a square minus b square will be the term, right? So remember that whenever such kind of multiplication is there, definitely its result is going to be a square minus b square, right? Okay, fine. So again over here j square, you don't forget about what is j square. J is imaginary term, and its j square is nothing but minus 1. So wherever the j square is going to come, you have to insert that as minus 1, right? So over here the j square was there and it has replaced by minus 1. So this minus sign has become plus over here, right? The numerator will not changed. Okay, similarly for this as well, j square has become plus, okay, over here, right? Fine. Then we are going to give the separate denominators to real term and imaginary terms. Okay, so for this, let us say RL, we have given the separate denominator, right? As well as for the this imaginary term, we have given the separate denominator. Similarly for this term as well, right? Fine. And then now we are going to club the real terms and imaginary terms, right? Okay, so we are going to now club the real and imaginary terms. Okay, so in this step over here, in this step we have clubbed the real terms and we have clubbed the imaginary terms, right? Okay, so let us take j common from this, let us say, imaginary term, and we have written this term at the first and then minus term at the next one. Fine. Now at resonance, remember that the XL and XC must be 0, right? So remember that at resonance, this imaginary term, this is sometimes also called as susceptance term. Okay, so the imaginary part of admittance is also called as a susceptance. Remember this thing. Okay, so at resonance, the susceptance part becomes 0, right? So for that purpose, we have to equate this with 0. Okay, and we did the same. Okay, so we have equated this to 0, right? Okay, now let us check out further to find out the equation of resonance frequency. So we are interested to find out the resonance frequency of a parallel resonance circuit. Okay, so after performing this, or after equating the imaginary term of y, we have got this term. Okay, so we let us transfer this minus sign term to the right hand side. Okay, and let us do some rearrangement. Let us do the cross multiplication. Okay, so this term we have transferred to the right hand side and this term we have transferred to the left hand side, right? And now let us do the some kind of rearrangement. So this is the condition at resonance. This is at resonance, right? So the frequency will represent or will have suffix as resonance. Okay, so xc is nothing but what, 1 upon omega c, right? And xl is nothing but what, omega l. So wherever the omega is there, you have to write the suffix as r. That's it. Okay, so that is the important thing you need to remember over here. Okay, so xc we have replaced by 1 upon omega c, but omega will have suffix as r because this is the condition at resonance. That's it. Okay, fine. Then RL square plus XL is nothing but omega R, omega L, right? So omega R into L, it's a bracket square, right? And similarly, this is also XL, we are going to replace with omega RL. Then same thing, we have replaced XC by 1 upon omega C bracket square, right? Okay. Now let us check out further. Now what we did, we just took the L and C at the one side and omega R at the another side. Okay, fine. And then now let us do some kind of again rearrangements. Okay, now let us multiply by 1 upon LC inside this bracket. Okay, and let us multiply by omega R inside this bracket. Okay, yes. And now we are going to club the terms of omega R. Okay, so that we can find out the resonant frequency. Okay, after multiplying this, we will be getting this step, that is nothing but RL square divided by LC plus omega square L square divided by LC. So this will get cancelled out, right? So L by C, omega R square L divided by C will be the remaining term, right? Okay, let it be. We'll see what we can cancel out. Okay, so omega R square, let us multiply by omega square inside this bracket. So RC square plus omega will get cancelled out. So 1 upon C square. Now what we did, we took the omega R term at the one side. Okay, so we took it at the one side, and this is nothing but now 1 upon C square. So this term we have taken at the left hand side, right? So this is as it is, we have taken over here, right? And the remaining is nothing but 1 upon C square only, and that term we have taken to this point, that is nothing but to the left hand side, and we have transferred this term to the right hand side. It is as it is. Okay, so omega R square into RC square minus omega R square. Now L we have cancelled out as like we did over here. Okay, so I think yes, we have taken directly that term and then we have cancelled out this single L. Is that fine? Now let us take out common omega R square from these two terms. Okay, so that we can easily find out what is the equation for resonant frequency. Is that fine? Great. Let us do this. Okay, so we took the omega R square common from these two terms. What are the remaining terms then? RC square minus L by C, right? Over here, now let us again take out the common from these two terms as L by C, 1 upon L by C, right? So we have taken common 1 by L by C, 1 by LC, sorry, not L by C, 1 by LC we have taken common from these two terms over here, and therefore LC is right now over here, right? But here only C square is there, so L has to be multiplied and 1C we are going to take out common. So this equation will have RL square minus L by C is equals to, after taking common omega R square, this has RC square minus L by C. Now let us transfer this term to the left hand side. So therefore 1 upon L by C is equals to RL square minus this L by C divided by RC square minus L by C. Remember that RL is nothing but the resistance connected to inductor, okay, and RC is nothing but the resistor connect in series with the capacitor, right? Don't consider that it is R into L, it is suffix, okay, RL, is that fine? So remember that this is suffix, it's not R into L, right? Okay, fine, don't get confused with this, okay? So suffixes are there, they may look like same, but their meanings are different, okay, fine. And this is nothing but the frequency, that is nothing but omega, we can take as a square root, okay. So 1 by root LC into root of this, okay. So this is nothing but my omega R. Now let us find out FR. FR is nothing but, now what is omega? Omega is nothing but 2 pi F. So it is nothing but 2 pi FR. Omega R is nothing but 2 pi FR, right? So let us insert that and let us find out the FR. Okay, resonant frequency for parallel resonance circuit. Okay. Yes. So we did the same and we have found out resonant frequency of a parallel circuit is nothing but 1 upon 2 pi root LC into under root of, okay, so we did the cross multiplication inside this bracket, okay. So C into RL square minus L divided by C is there, right? This also RC square into C minus L divided by C. So we can cancel out this C and this C. So this equation gets modified or simplified as like this. Okay, what is this? This is the resonant frequency of a series RLC circuit. So, or if I am going to insert R by RL is equal to RC, if the values of resistors connected in series with the capacitor and inductor, if they are having the same value, then this equation will result to, this is going to become 1. Okay, so therefore it is nothing but FR is equals to 1 upon 2 pi root LC. Okay, fine. Okay, so till then we'll stop over here and we'll continue in the next lecture. Okay, thanks for watching. Okay, now let us check the another type of circuit, that is nothing but tank resonant circuit. Okay, so this type of circuit is also called as resonance circuit, okay, in which again the inductor and capacitor are connected in parallel, but there is a only single change that there is no resistor connected in series with this capacitor. Okay, fine. So this approach of deriving the equation will be same as that of your parallel resonance circuit. Okay, fine. So remember that over here also we need to find out the impedance of this arm, then impedance of this arm, then we are going to take its admittance and then we are going to club their add their admittances to find out the total admittance of the circuit. Okay, so let us do the same and then we are going to equate the imaginary term of that let us say impedance, that admittance equal to 0, right? Let us do the same. So y1 is nothing but 1 upon RL plus JXL, right? And y2 is nothing but simply it is having 1 upon minus JXC, right? It is not having any kind of series resistance. So let us add these two, y1 and y2. Okay, so we are going to add y1 and y2. Is that fine? So we have inserted y1 over here. We are going to insert y2 over here, right? So therefore it is nothing but 1 upon RL plus JXL plus 1 upon minus JXC. Okay, fine. So this minus JXC minus sign we have written at the center. Okay, that you know very well. No need to discuss that again. Okay, great. Now what we did, as we used to do, we are going to do multiplication of, we are going to multiply and divide by complex conjugate of this denominator term. Okay, and that is nothing but we have taken directly. Okay, so we have skipped the middle step and we directly did the a minus b bracket square, a square minus b square, sorry. Okay, and this will be as it is. We are not going to change anything for this. Okay, fine. Only the denominator j we are going to get cancelled out by simply multiplying by and multiplying and dividing by j. Okay, so for that purpose only we did the multiplication and division of j. Okay, great. So we have replaced minus j by, sorry, j square by minus 1. So this middle sign is going to become plus. Okay, and this we have multiplied by and divided by j. Okay, so therefore this j square is going to become now minus 1, and because of that this minus sign has changed to plus. Okay, again give the separate denominator to the real and imaginary term. Okay, fine. So we did the same. Okay, we have taken the separate denominator for real term, and this is nothing but the separate denominator for imaginary term, and this is as it is. There is no change. Okay, now club the terms, imaginary terms together. Okay, so therefore j inside this bracket, this we have taken over here 1 upon jxc minus sign as it is. Okay, and we have taken this term to the this point, and the condition of resonance is what? At resonance the susceptance part, that is nothing but the imaginary part of my y, is going to become 0. So that is meaning by we are going to equate it to 0, right? Fine. So let us equate it to 0. I hope you are understanding this one. Okay, it is very easy actually. Okay, so we have equated this term to the to 0. Okay, now let us transfer this term to the right hand side so that we can cancel out this minus sign. Okay, so we have transferred this. Now let us do the cross multiplication. We are going to take this term to the right hand side, left hand side, and xc we are going to get multiplied with xl, right? Okay, now wherever there is a xl and xc we are going to put as omega r into L. Okay, and xc is nothing but 1 upon omega r c, right? Okay, so that we can okay, after putting this xc as 1 upon omega c and xl as 1 upon omega L, we can cancel out omega omega terms. Let us put xl as omega L over here. So over here we have inserted it. Okay, so this is the only term after L by C. Okay, so these are the remaining terms. Okay, so L by C is as it is, and left hand side is nothing but RL square plus XL square. Now instead of XL we are going to put it as omega L. So therefore RL square plus omega square L square is equals to L by C. We need to keep omega on the one side, so let us transfer this to the right hand side. Therefore L by C minus RL square is the term. Okay, again transfer this L square to the left hand side. Okay, let us do the same and let us check it out, and finally we'll derive one equation. Okay, so over here what we did a cross multiplication. So L by C was there minus RL square, right? So L minus C RL square divided by C. Okay, and once we are going to transfer this L square to the right hand side, then it will be get into the denominator, so L square. Okay, is that fine? Great. Now let us check out further. Keep in mind. Okay, great. Then okay, so after that what we did, we given the common denominator separate to all. Okay, therefore it is nothing but this single L and this L square is going to get cancelled out, so therefore it is going to become L 1 upon L by C, and this C get cancelled out, and therefore it is nothing but RL divided by L square. Okay, RL square, sorry, this is nothing but RL square. Okay, so RL square divided by L square is nothing but this term, right? And then we took the square root, therefore omega r is equals to 1 upon root 1 upon root sorry root 1 upon LC minus RL square divided by L square. Okay, and let us find out FR then. So we are going to put omega r as 2 pi FR, and because of that we are going to get the final equation as 1 upon 2 pi FR is equals to FR is equals to 1 upon 2 pi root 1 by LC minus RL square by L square. So this is the equation of resonance for tank circuit. Got it? Okay.